Now, we will try to understand the relationship between latent heat of fusion and latent heat of vaporization with the help of a diagram. Let us see. So, dear students, we will try to understand the relationship between the latent heat of fusion and latent heat of vaporization with this particular diagram. Here in this diagram, you can see that along the x-axis we have put time in terms of minute, and along the y-axis it is reflecting the increase of temperature. So we will try to see the journey of ice and how it changes its state as we increase the temperature with respect to time. Well, the journey begins at A, and when we go on increasing the temperature, we see that, as I had explained to you earlier, there is a change of state from ice to water. But at a particular temperature, we see there is complete conversion of ice into water. But have you noticed one thing? At that particular temperature, we don't see much increase, okay? Although we have increased the heat, okay? Now, as I told earlier, where has that heat come? That heat was spent to break the shackles of attraction between the particles of ice and convert it into water. So, along the phase from B to C, you don't see increase of temperature. So that particular temperature, which is reflected as T1 here, is the latent heat of fusion. Then again, at C, when there is complete conversion of ice to water, the journey of water begins from here. How it reacts when it is exposed to higher temperature or heat, okay? So it is almost similar to how the changes took place with respect to ice. At a particular temperature, which is reflected in this figure by T2, we see conversion of water into water vapor. So this particular temperature at which there is conversion in bulk from water to gas or water vapor, it is known as latent heat of vaporization. So how do we sum up our learning so far? We will try to understand whatever we have learned till now with the help of a particular table. Look at the table. Here we will try to understand the characteristics of solid, liquid and gas. Okay? Now, if we look into the factor of force of attraction between particles, what we understand is that it is maximum in case of solid, intermediate in case of liquids, and the forces of attraction between particles is minimum in case of gas. So the observations are similar with respect to kinetic energy of particles too, as well as the space between the different particles of solids, liquids and gas. Now let us look into the arrangement of particles in solids, liquids and gas. As I have told you earlier also, in case of solids, the arrangement of particles is most ordered. In case of liquids, it is less ordered with some randomness in between. But in case of gas, it is very random. So dear students, what have we understood from this discussion so far? We could learn that as we increase the temperature, there is a change in the state of matter from solids to liquids, as well as from liquids to gas. But here, I would like to put one question to you. Do you know of any substance which can change directly from solid to gas? Is there any phenomena like that? Well, let us try to do another activity to understand this. And the substance that I will take here, ammonium chloride. Right? So, let us take a little camphor or ammonium chloride. Let us understand how to do this particular experiment. As I told you, we have taken a little bit of camphor or ammonium chloride and we have put this on a china dish and then we will heat it. And what we will notice is that these solid particles of camphor has vanished, but we don't see any liquid here. And what we see is that it has all got converted into gas. So this is a phenomenon where the change of state has taken place directly from solid to gas. Now, do you have any idea what this phenomena is known as? This is known as sublimation. So finally, dear students, I hope you all have understood what I tried to explain, how the change of state takes place in matters as we increase the temperature.
You have taken out more, only 1 centimeter.
So you can focus it here. So dear students, are you able to notice one thing? Earlier this beaker was full of ice, 150 grams, and as we lit up this spirit lamp, the temperature started to increase, and because of that the ice started to melt. And along with the melting of ice, we still have, I think, a few pieces of ice and which will eventually melt. And as the ice are melting, the temperature is increasing, and now if you see earlier, the temperature which was at 0 is now increasing. Do you see the red mark here? The temperature is increasing and eventually the ice is slowly and slowly changing its state from the solid state, and what we see is water. And if we continue it like this, you will see that at one point of time, when the temperature will increase and it will be close to 100, you will see bubbles here. You will see gas coming up, water vapor. These things I think you must have noticed when your mother was preparing a cup of tea in the kettle, right? So that way, you know, the water vapor starts to come up. Okay? And what we see from this experiment is that as we increase the temperature, there is a change of state from ice to water and from water to eventually gas. Now you see what happens as we increase the temperature. The kinetic energy of the particles starts to increase. And as the kinetic energy of the particles starts to increase, the particles start to vibrate randomly. They start to move randomly. Is called freezing, and the reverse process is called melting. Number C. The transformation of liquid to solid is called melting, and the reverse process is called freezing. Number D. None of the above. The answer is option number A. Question number 5. The temperature at which solid and liquid coexist in equilibrium is called A. Melting point of liquid, B. Freezing point of liquid, C. Freezing point of solid, and D. All of the above mentioned. Yes, the answer is option number B. Well, tell me, the melting point of ice is, your options are A. 0 degrees centigrade, B. 100 degrees centigrade, C. 4 degrees centigrade, and D. -4 degrees centigrade. What should be the answer? Well, the answer is option number A. Let us move to the next question. At which temperature does water freeze? The options are A. 0 degrees centigrade, B. 100 degrees centigrade, C. 212 degrees centigrade, and D. 32 degrees centigrade. It's quite easy, isn't it? The answer is option number A. Boiling.
Tên itu tên dia yang nyoring. Tên bằng ý mà tên hiện tên phai sẽ bằng ý cái gì tụi nó phai sẽ ý là
should we bring some hot water?
Hot water?
Hot water from some kettle, electric kettle.
If it's dead. Ý Thì trong sao?
Thì nhẹ thế hả? Tập lại cho kinh.
Question number 9. The force that binds the particles of matter together is known as option A. Intermolecular space, option B. Bond, option C. Intermolecular force, and option D. Nuclear force. Yes, what should be the answer? Right, the answer is option number C, that is intermolecular force. Let us look into the next question. Amount of energy required to change the liquid to gas and vice versa without any change in temperature is termed as, your options are A. Latent heat of fusion, B. Latent heat of vaporization, C. Heat capacity, and D. Specific heat capacity. The answer is option number B. Question number 11. When we hang our washed clothes to dry in a string outside, it dries faster even if there is no sun. This is due to option number A. Boiling of the perfume, B. Evaporation of the liquid, C. Melting of the liquid, and D. Condensing of the deodorant? Well, the answer is option number B, evaporation of the liquid. Let us look into question number 12. Unit of specific latent heat is option A, watts per joule, option B, joules per watt, option C, joules per kilogram, and option D, Pascal per watt. The answer is yes, it is option number C. Now, question number 13. Latent heat of vaporization is, your options are A, the amount of heat required to raise the temperature of a 1 kg of a substance by 1 Kelvin. Number B, the amount of heat required to raise the temperature of a substance by 1 Kelvin. Number C, the amount of heat required to change the phase of a substance from solid to liquid without any change in temperature. And number D, the amount of heat required to change the phase of a substance from liquid to gas without any change in temperature. Yes, the answer is option number D, that is, the amount of heat required to change the phase of a substance from liquid to gas without any change in temperature. Let us now move over to question number 14. Specific latent heat of fusion is, the options are A, the amount of heat required to raise the temperature of a 1 kg of a substance by 1 Kelvin. Option number B, the amount of heat required to change the phase of a substance from solid to liquid without any change in temperature. Number C, the amount of heat required to change the phase of a 1 kg of a substance from solid to liquid without any change in temperature. And number D, the amount of heat required to change the phase of a 1 kg of a substance from liquid to gas without any change in temperature. Yes, tell me. Right, the answer is option number C, that is, the amount of heat required to change the phase of a 1 kg of a substance from solid to liquid without any change in temperature.